Have you ever wished you could just go backwards in math? You get an answer and you want to know exactly what number you started with to get there? Well, that's exactly what inverse functions are for. They are basically the undo button for math, and today we're going to figure out how they work. Normally, math is a one-way street, right? Think of it like a coffee machine. You put in the coffee grounds, that's your input. You press a button, and the machine does its thing, that's the function, and then you get a delicious cup of coffee. That's your output. Simple. Input, process, output.
But what if you worked the other way? What if you were handed that cup of coffee, and you needed to figure out exactly how many coffee grounds went into making it? Or you know your final destination, and you need the exact starting address. That's the problem inverse functions were born to solve.
So let's look at this visually. A function, we'll just call it f, is kind of like a bridge. It takes a number, let's say a, from its home in set A, and carries it over to a very specific spot b, over in set B. So f of a equals b. Straightforward. And here's the cool part. The inverse function, which we write as f with a little -1, is the return trip. It's the bridge going back. It scoops up b from set B and takes it right back home to a in set A. It perfectly undoes the original journey. So if f of a equals b, then f inverse of b has to equal a.
But there's a catch. Not every function gets its own personal undo button. There's a really important rule that a function has to play by, and it's called the one-to-one rule. Let's see why this is such a big deal.
Okay, take a super common function, f of x equals x squared. If you plug in 2, what do you get? 4. Easy. But what if you plug in -2? You also get 4. So think about it. If I just tell you the output is 4, can you tell me for sure what number I started with? Nope. Was it 2 or was it -2? That confusion means we can't make a reliable undo button.
And that leads us to the solution. The function has to be one-to-one. This is the golden rule. It just means that every output has one and only one input that it came from. No confusion, no ambiguity. It gives us a clear path back to where we started.
And you know what? There's a super simple way to see if a function follows this rule. It's called the horizontal line test. All you have to do is imagine sliding a horizontal line up and down the graph of your function. If that line ever, at any point, touches the graph in more than one spot, like it does for our x-squared graph, then it fails the test. It is not one-to-one.
Okay, so we get the why. Now let's get our hands dirty with the how. How do we actually find the formula for an inverse function? Well, luckily, there's a really clean algebraic recipe we can follow.
It's a pretty simple four-step process. First, just to make life easier, we replace the f of x with a y. Second, and this is the most important part, you literally swap the positions of x and y. This isn't just a gimmick, it's the actual math move that represents reversing the input and the output. Third, you just use your algebra skills to solve for that new y. And finally, you give it its proper name, replacing y with the f inverse notation.
Let's walk through one together. Let's say we have f of x equals 3x minus 2. Step 1, y equals 3x minus 2. Got it. Step 2, let's swap them. Now we have x equals 3y minus 2. Step 3, time to solve for y. We add 2 to both sides, then divide the whole thing by 3, which gives us y equals x plus 2 all over 3. And step 4, we just label it properly. The inverse function is f inverse of x equals x plus 2 over 3, and that's it.
So, you've found the inverse, but how can you be 100% sure it's right? And what are the common traps that people fall into along the way? Let's cover how to double-check your work and steer clear of those little mistakes.
This right here is the ultimate proof. If two functions are truly inverses, then when you plug one function inside of the other, that's called composition, they should basically cancel each other out, leaving you with just x. And here's the kicker. It has to work both ways. If f of g of x equals x, and g of f of x also equals x, you know you have a perfect pair.
There's also a really cool visual check. Because an inverse function swaps all the x and y values, its graph ends up being a perfect mirror image of the original function's graph. And the mirror is that diagonal line y equals x. If you graph both and they don't have that perfect reflection, you know something's gone wrong.
All right, let's talk about those common mistakes. First, a classic, forgetting your parentheses. It's a small thing that can cause big problems. Second, if you're solving for y and it's in a few different places, remember you'll probably have to factor it out to get it alone. Third, with functions like square roots, sometimes the inverse needs a domain restriction to make sure it's still a valid function. And finally, please remember, that little -1 does not mean exponent. F inverse of x is not the same thing as 1 divided by f of x. Totally different concepts.
So, why do we even bother with all this? Is it just a mental exercise for math class? No way. Understanding inverse functions is a fundamental piece of the puzzle that opens up so much more. You see, mastering inverses is what lets us understand things like logarithms, which are just the inverse of exponential functions. This is the math behind cryptography that keeps our information safe online. It's critical for solving equations in engineering and physics, and it's an absolute cornerstone of calculus. It's a concept that just keeps coming back, stronger every time.
And that brings us to one last thought. We use inverse operations all the time without even thinking about it. Subtraction undoes addition. Division undoes multiplication. So the question to leave you with is, what other, maybe more complex undo buttons are hiding in plain sight all around us? Something to think about.